So last class we discussed about this point collocation method. So what do you mean by a point collocation? So first we discussed what is a mathematical model, and we introduced something called as a trial function. Using the trial function, we identify a residual, and our aim is to reduce that residual, right? That is our main aim. So the first method what we used is that point collocation. So what we do is we take a point in between the structure, right? Any point in the structure, and we say that that is equal to your exact solution, which means your residual is equal to 0. So when you do that, you can able to approximate it so that based on number of points, if you increase the number of points, your value will be closer to your exact solution, right? So that is the first method. The second one is subdomain collocation, right? So we will discuss about this. So subdomain is accurate when compared to point collocation, right? So point collocation is the first one. So after that, it has been again it upgraded, like a software. It has been upgraded, and they went for this subdomain collocation, right? So the subdomain collocation is also the same thing. So you're based on the number of residuals. What I'm going to do is I'm going to integrate the domain, right? Which means I have to integrate the R of x, right? Based on the particular domain, I'm going to integrate it, and I'm going to equate it to 0, right? So that is the only difference in subdomain collocation and point collocation. Point collocation, I say that some value R of x is equal to 1 point and equating to 0. Whereas this subdomain is I'm integrating it, right? Once I integrate it, and then I'm going to apply that is equal to 0, right? So when I integrate, I get to split it accordingly. So 0 to 1 by 2, 1 by 2 to 1, something like that, based on how many number of unknowns you have, right? Your integral domain will also change accordingly. So this is the formula, right? Integral domain integration of R of x is equal to 0, right? So if I put just R of x is equal to 0, it means point collocation. Integrating of R of x is equal to 0 is subdomain collocation, right? So this DI indicates number of domains, right? For example, if you are unknown, I have only one unknown, A1, which means my domain, my limit is from 0 to 1. That's it, 0 to 1, R of x is equal to 0. If I have two unknowns, so A1, A2, right? And my overall boundary is from 0 to 1. I'm going to split this domain into 2, which means 0 to 1 by 2. And then another domain is 1 by 2 to 1. That is, we are going to split it accordingly. And then we will equate it to 0. So what is the difference between these things? So this is the graph you can able to see. So you can able to see a brown color line, right? That is my exact solution. This is my exact solution, right? So when I apply point collocation, so I say that at a particular point, it is equal to your exact solution. Let me consider some points. So at x is equal to 0, at x is equal to some other point, at x is equal to some other point, at x is equal to some other point, and x is equal to some other point. And that point alone, you can able to see that your solution, whatever your approximate solution, the blue color line is the approximate solution. It is matching with respect to that. Okay. So what the problem here is in point collocation, sometimes it may be like this also, like your curve. So it starts from 0. These 2 points are matching, but in between you may have a curve like this also, like this. It may go like this, right? So you can able to see there is a high peak, and then it is coming at that particular point alone. It is exact solution, which means this is not equal, right? You can't able to justify. I can't say that your point collocation will give the exact solution. It's the real part you can use that. That is not possible. So because of this particular thing, so there may be a high peak, right, in point collocation. So in order to avoid that, what they've done is they're going to use this integration part. Integration is I'm considering this area, and the other area, I'm integrating and equating to 0. When I integrate, what happens? This peak is reduced. Instead of higher peak, your peak will be reduced. So that your area integration will be somewhat equal, so that I can able to get similar to it, nearer to your exact solution. So that is the main purpose of this subdomain collocation. Subdomain is I'm integrating, which is reducing the peak. Okay, so reducing the peak with respect to your exact solution. Okay, then we proceed with the same problem what we discussed last class. So you consider this problem, d square y by dx square plus 50 is equal to 0. So under the limit 0 to 10. So this is the same trial function we are considering. So y is equal to a1x into 10 minus x. Okay, same problem, right? So but I'm going to solve it by using subdomain collocation. So first I checking my trial function. It will satisfy the boundary condition because we already verified it in last class. So I will take the trial function. I'm going to substitute this trial function in this equation. So which means I have to differentiate this twice. Same procedure. So dy by dx, d square by dx square. So I'll get minus 2a1. Substituting in this, you will get this. This is your r of x. Up to this is same. Whether it's a point collocation or subdomain collocation, or even in least square and other methods also, the up to this is same. Right? R of x. We identify up to r of x. The next step is different. Okay, so how many unknowns are here? You have one unknown. So since you have only one unknown, my limit, I am going to integrate this with one limit, which is from 0 to 10. Okay, I'm not going to split my integration. 0 to 10. If you have two unknowns, what I have to do? I have to integrate 0 to 5 and then 5 to 10. So one integration is 0 to 5. Other integration is 5 to 10. And I will equate it to 0. Okay. So let me consider it here. So you have only one unknown here. So let me consider the limit is 0 to 10. So I'm going to put the limit. Integral 0 to 10 r of x dx is equal to 0. What is my r of x? I know what is my r of x. R of x is minus 2a1 plus 50. So into dx is equal to 0. Integrating this, what you'll get? You don't have any x term here. So when I integrate, I will get one x. I skipped some step. I will write it here. So what you'll get? You will get minus 2a1 plus 50 into x. The x will have a limit from 0 to 10. This is equal to 0. Right? What you'll do? I will substitute the value. You will apply upper limit and lower limit. What you'll get? I will get minus 2a1 plus 50 into 10 is equal to 0. So cross multiplying, what will get? This 10 when you cross multiply it becomes 0. So what I'll get minus 2a1 plus 50 is equal to 0, which means again I will get a1 is equal to 25. Right? No difference. Right? So which means my solution is same what we discussed. So y is equal to 25x into 10 minus x. So a1 is 25. Right? I think we got the same answer for point collocation also. So let me go for the next one. This is subdomain. So same problem. So now you have two unknowns. Right? I consider the same trial function. I'm going to substitute in my equation. So I will get what is my r of x. So up to this is same. So now if I verify this equation, I got two unknowns, a1 and a2. There are two unknowns here. Okay. So what I have to do, I have to split my integration as 2, right? Which means 0 to 1 by 2 is one integration. Other integration is 1 by 2 to 1. This is my other integration. Okay. So let me consider the first one. The first domain is 0 to 1 by 2. So integral 0 to 1 by 2. Right? Limit is 0 to 1 by 2. R of x dx is equal to 0. So what is my r of x? I substitute all my r of x here. Integrate this. So when I integrate, I will get, okay. So let me do it here. So what will get? I will get minus 6a1. So x, if you integrate x square by 2 minus 20a2 x cube. If I integrate, you will get x power 4 by 4 plus 500 x square. If I integrate, I will get x cube by 3. All are removed from 0 to 1 by 2. 0 to 1 by 2. Right? And 0 to 1 by 2. When I substitute and equate it to 0, you will get this as an equation. So first term is over. Second, what I am going to do? I am going to integrate from 1 by 2 to 1. No. Okay. So I am splitting into 2, right? So 0 to 1 by 2. Now 1 by 2 to 1. So since we have two unknowns. Okay. So what I do, let me substitute it accordingly. So whatever the integration it is, so integrate it, right? Integration is same. Only thing is I have to apply the limit. So previously you don't have lower limit. Lower limit is 0. But here you have upper limit and lower limit. So which means 1 minus 1 by 2. So you will get something like that. So when you do that integration, you will get another equation. That is equation number 2. Now you solve this 2. So you have two equations, two unknowns. Solve this 2. You will get what is the solution. So A1 we identified, A2 we identified. Substitute it in your trial function equation. You will get your solution. So this is subdomain collocation. So this is the procedure for this subdomain collocation. So what happens if you have three unknowns? What
We need
happens if
to
you have three unknowns?
domains to 0 to 1 by 3 and 1 by 3 to 2 by 3 and 2
Yeah.
by 3 to 1.
So very good. So it is from 0 to 1 by 3, then 1 by 3 to 2 by 3, then 2 by 3 to 1, right? R of x dx is equal to 0. So all are same. R of x dx is equal to 0. R of x dx is equal to 0. So you'll have three unknowns, three equations. You should solve this three. You will get the solution. Okay. So hope. So the procedure is same. Only thing is I have to integrate. So least square method is same thing, but I am going to introduce one more wi. This wi we call it as a weighted function, right? This wi is weighted function. So why we introduce this? The reason is at a particular stage. So you know that. Let me consider. So we saw a mesh, right? So let me consider. You have an object here which is going like this, and then you have a curve like this. Okay. So if I mesh this in ANSYS or whatever software, right? So since you have a curve here, right? So you know that your element will be less here. So something it will go like here. So here the element will be very less, small elements, because in order to occupy that curve, right, you have small elements, then you will have bigger one, right? So this one, there is a difference in the elements, right? Okay. So in order to give more accurate answer, we give this as a weighted function, right? We will give this as a weighted function, right? So what I'm going to do to get more accurate, I'm going to give an weighted function. So I say that this location, I need some weight. So that weight is some error. So I'm going to rectify that error. To rectify my error, I am multiplying something. Okay, so that is what we call it as a weighted function. So I introduce that weighted function, and that weighted function is dou r by dou ai, right? Which is partially differentiating your residual in terms of your constants, right? In terms of your constants. If you have a1 as a constant, partially differentiate your residual in terms of a1. Whatever the value, you multiply it here along with r of x and equate it to 0. Right? Here the domain is same. When I say domain is same, it is always when the limit is from 0 to 1, the limit is 0 to 1. Okay? But this one will change. W1 is dou r by dou a1. W2 is dou r by dou a2. Right? This will change, but this thing doesn't change. Right? In order to avoid this problem, right, we introduce this. Okay? So that it will be more accurate answer. Okay? So as I told you, this is more accurate when compared to your subdomain. So we will solve the same problem related to this two problems. The first problem, again, you have r of x. Hope you know how to get this r of x, right? So you have a trial function, differentiate this twice and substitute it in this equation, you will get this R of x. Now, this R of x, right? You have only one unknown. Since it is having one unknown, you have weighted function W1 alone. Right? What is this W1? W1 is dou Rx by dou A1. Since this is the unknown value, so I am differentiating with respect to that A1. So what you'll get? So when I substitute, so dou R by dou A1. So of this one, what I'll get? I will get -2. Okay, this I have to multiply with your R of x. I'm going to substitute this here, right? So W1 I got it. R of x is same value. Dx I'm going to equate it. Okay. So -2 of -2a1 plus 50 dx is equal to 0. My limit is again 0 to 10. Don't need to split our limit. Okay. So it is same. So when I do this, what we'll get? We'll get again a1 is equal to 25. No change, because when I use only one trial function, there won't be much change. Right. So that is my answer. So this is least square method. Okay. Right. So let me go for the next one. So this one, which is having two trial functions, you got what is your R of x? Your R of x is -6a1x minus 20a2x cube plus 500x square. Here you have two constants, so two unknowns, so 1 and 2. So which means I have two weighted function, w1, which is dou r by dou a1. Other thing is w2, which is dou r by dou a2. So both function, first one, integral 0 to 1, limit I am not going to change, 0 to 1, w1 r of x dx, where w1 is dou r by dou a1. So when I put dou r by dou a1, what I'll get? I will get -6x, right? I will get -6x. So multiply this -6x with your r of x. So when I multiply, I will get some other term, and then I'm integrating it. I am getting your term. So I'm getting a1 plus 2a2 is equal to 62.5. So I'm not solving this. So when you do this and integrate it, after you apply your limit, you will get this. This is equation number 1. Next. So 0 to 1, limit is same. Now W2 R of x dx is equal to 0. W2 is dou R by dou A2. So when I take dou R by dou A2, what you will get? I will get 20x cube. So -20x cube. So I'm multiplying with your R of x. Again, when you do multiply it, so applying your limit, everything, you will get another equation. So this is equation number 2. So solve these two equations, you will get what is your solution. So that gives your solution. The last one is Galerkin method. So there is no much difference between least square and Galerkin method. Procedure is same. Only your weighted function is different. So previously what I did, I consider weighted function is dou R by dou A. Here the weighted function is dou U by dou E. Instead of going for your residual, I am using my trial function. I am differentiating my trial function. This is my trial function. This is residual. Least square is you are partially differentiating your residual, whereas Galerkin method is you are partially differentiating your trial function. Okay, so trial function is the what you got it at the beginning, right? That one I am integrating and again multiplying it and equating to 0. The procedure, all the procedure are same. So that's the only difference. So this is more accurate method. This is the only method which is very helpful in minimizing the conditions. So most of the FEM nowadays it comes under this method, which is converted in terms of matrix. Right, the method is converted in terms of matrices. Okay, so I'll consider the same one. So you have your R of x, one unknown here, which is a1. Okay, so since I have a1, which means I have w1, which means I have w1. So one weighted function. What is that weighted function? Dou y by dou a. dou a1. So since you have a1, so dou y by dou a1. So this is my tail function. I have to differentiate this now. What will get? I will get w1 is equal to a1 partially differentiating. This will become 1. So remaining terms, I'll get 10x minus x square. 10x minus x square. This I have to multiply with your r of x, integrate it, and then equate it. Right? So that's the thing. So you can able to see here 0 to 10 w1 r of x dx is equal to 0. So w1 is dou y by dou a1. So which means I will get 10x minus x square. So then you substitute that in this. So this I am substituting here. So 10x minus x square into r of x is you already know. Multiply it and then integrate, apply your constants. So you'll get 25. No difference. Okay. So when you do that, you'll get the same answer. So which means your y is equal to 25x of 10 minus x. So let me go for the next one. So it's having two trie functions. So you know what is my r of x. So we substituted to get r of x. In r of x, I have two unknowns, a1 and a2, which means I need w1, which is dou y by dou a1. When I partially integrate, so differentiate this dou y by dou a1, what I'll get? I will get x minus x cube. That is my first term. Next, I have w2, which is dou y by dou a2. Right? So when I partially differentiate it, I will get x minus x per 5. This is my next term. So these are the things I have to multiply. So 0 to 1, w1 r of x dx is equal to 0, substituting it. So w1 is equal to dou y by dou a1. So you will get what is your partially differentiate value. So I will erase this because it will be disturbing. Yeah. So next, multiply with your r of x. You get a whole term like this. Then integrate it. Okay. So apply your limit. So when you do that, you will get this as a value. This is equation number 1. Similarly, you go for w2 r of x dx is equal to 0. So dou y by dou a2 is equal to 0. So just identify what is the values with respect to that. Again, multiply this overall term, integrate it. So once you integrate, you will get this as a second equation. Solve this two, you will get your solution. These are the overall methods. Okay. So when I consider these things, so I am comparing all the 4 methods with respect to problem 1 and problem 2. Right? So problem 1, all are same answer. Why? So you have only one unknown. Tail function has only one unknown a1. Problem 2, right? So this is the variation, the solution variation. Just I'm substituting this, I'm making as a graph, right? So problem 2, you can able to see this is my problem 2. You can able to see the difference. So at this beginning it is 18. So slowly it is increasing. There is a lots of difference with respect to these things. So which is you can able to see that this is more approximate. When I plot it, you can able to see something like this. Your graph will be like this. So this is my point collocation. So point collocation, subdomain collocation, least square is very less. So Galerkin is in between. Okay. So most of the time, so according to, so we can't conclude it directly, right? It is from the research, right? From the research, it is concluded that Galerkin is best method, right? So when compared to all the 4 methods, okay? So Galerkin is the best method. Okay, there are something other terms also that we will discuss it. So Galerkin makes your differential equation to a weak form. It will weaken your differential equation. These things we will discuss it, right? So once we complete we will solve one problem related to this, right? After that we will proceed with respect to that.